Now for example number 2, you're given a pure gaseous reactant A. Initial concentration is 100 millimole per liter, which is fed at steady state or into in a steady rate into a mixed flow reactor, volume zero point 0.1 liter, where it dimerizes using the reaction 2 moles of A forming 1 mole of product R. Now, for different gas feed rates, the following data are obtained. So there were 4 runs that were made. So for run number 1, you're using a different volumetric flow rate, and it was observed that this is the corresponding final concentration of A for this particular run. So you started with 10 liters. You use rather 10 liters per hour of feed. For run 2, you use only 3. For run 3, you have 1.2. And for run 4, you use zero point 0.5. Correspondingly, you could see also a trend that if there's a decrease in the volumetric flow rate that is being processed by your reactor, correspondingly, there is also a decrease in the final concentration of A unreacted, that is. So you are to find the rate equation for this reaction. So the rate equation can first, of course, be in the form of a rate law, but later on that rate law can be written in the form of a rate equation in which the left side, the RA expression, is converted into a derivative form. And that is the derivative of the change of the concentration of A, with of course with respect to time. So you have one requirement, and these are your given information. Oh, sorry, that's already the key points from this particular um, problem. So let me, where's my pen? Let's go back to our board. So you have the reaction 2A forming 1 mole of R, and you're started with a certain volume and a certain initial concentration. So let me go back to the problem first. I was not able to get a picture of that particular problem. So this is our problem. Your volume in this case, the volume of the reactor is 0.1 liter, and your initial concentration is 100 millimole per liter. So it's a pure gaseous reaction starting with A. So this is a gas reaction. This is very important that you take note that it's a gaseous reaction starting with pure A. And that you're given this particular tabulated data for 4 different runs. So you have the concentration in millimole per liter, and you have the volumetric flow rate in liter per hour. Okay. So you have for 10, you have 85.7. For 3, you have 66.7. For 1.2, you have 50. And for 0.5, you have 33.4. Okay, so this reaction is to happen in an MFR. So it should be a mixed flow reactor where this particular reaction should happen. Now, you are required for the rate equation. You can start with the rate law, then just change the rate expression in the form of the derivative. So these are our given information on that particular problem. And of course, so let us start with the solution. You already started actually with the solution by writing down your understanding of what is given in the problem and what is being required. But as to starting on finding what is being required by the problem, that requires you to, so what do you think should be the first thing that I should be doing here? I'm now trying to find the required information, and that's the rate equation. So I need to start with the what in this case? Do I need to start with, or where do I start finding the required information? You can place it on the chat box, or you can, if you have your phones, you can interact with me through your phones. How do I start the solution of this problem? So there's 20 of us, 6 of you not around. Anyone? How do I solve this? I need to find the rate equation. And we're talking about the mixed flow reactor in which we're provided with this information. So these are the information that is given. So if you are the student, how would you start solving the problem? I'd like to know if you have the idea on what will you do. Anyone? How do I start solving the problem? Aliana, any suggestion on how am I going to start solving the problem? Aliana, how do I start solving the problem? Aliana is not around. Aliana?
Hindi ko kabalo.
Okay, sige. So, what about Antoinette? Antoinette, how do you start solving the problem?
Afternoon, Miss.
Pardon.
Required the Miss rate equation, Miss no palimit.
Mm-mm.
Miss establish the Miss relationship, Miss at given Miss in ano man.
Ano idea, Nay? Si Arnica, base si Arnica. Arnica, how do I find the rate equation, Arnica? Arnica, are you there?
Pwede ka start niya sa negative RA equal to CAO dxa dt or
I will start with what? RA equal to?
hindi ko siya sure, miss. Pero ang negative RA equal to CAO gamis ng equation na.
Oh, let's see. I will ask Colleen. Colleen Awit. How do I start? Pa si Colleen. Colleen, how do I start? Or Colleen.
Hello, Miss. Sorry,
Yes.
bago lang ko nagkabalik kay connecting.
Sige, sige. I was actually looking for you, asking a question. Have you followed through starting from the given, no? Nadula ka?
Ara ko, Miss.
Ara
Sige.
ka, okay. So how do you think should we start solving the problem?
Um,
We are given 4 sets of data for 4 runs, and we are asked to determine the rate equation. What do you think should we do?
find the expansion factor, Miss.
Find the expansion factor, the epsilon A.
Ang EA bala, Miss.
Ang epsilon A. Is that what you mean?
Yes, Miss.
Okay, sige. So we can start with that. So that's the suggestion of Colleen. However, you can actually start with the main equation. That way you would know what you look for. But nonetheless, Colleen has a point of starting with epsilon A because we have written here that we are given a gaseous reaction, and so as not to commit that gravest mistake of forgetting that whenever your reaction is gaseous in nature, you have to determine the fractional change in the volume or the expansion factor that Colleen was saying. So that expansion factor can be determined using the formula. So epsilon A is equal to, so let's see if you haven't forgotten due to the long vacation, the epsilon A. What is the epsilon A formula? Renzo, what's the epsilon A formula?
Wait lang, Miss.
So Giselle mentioned that it will start with the expansion factor. So you're right. You have the same way of thinking with Colleen. So when we speak of, okay, Renzo, I will write here, the formula of determining the expansion factor or the fractional change in the volume is you account for the volume at 100% conversion, you subtract the volume at 0% conversion divided by the volume at 0% conversion. Is that right, Renzo?
Yes, Miss.
Okay, so this is our formula for determining the fractional change in the volume or the expansion factor. Now, in that sense, we need the volume at 100% conversion. Now, in our problem, it says that we started with pure A. Okay, so whenever we start with a pure component, that makes things a lot easier for us in terms of determining the expansion factor. So can you dictate to me how do we determine the epsilon A given the scenario that we started with pure A? So let me see. Can we have Kenneth Abidejos? What should I write here for the volume at 100% conversion and the volume at 0% conversion? So since we started with 100% pure A. Kenneth? Oh, si Giselle. So, yes, Kenneth?
Ang sa B sa XA equal to 1 is equal to 1.
1 minus
Ang sa 0, ano is 2.
2 over 2. So if you are given a pure species, gaseous species that will react, your expansion factor is simply the difference with the coefficient of the product minus the coefficient of the reactant. If you have several, you need to add all the coefficients divided by the coefficient of the reactant. So in our case, it's 1 for our product R and 2 for our reactant A. So that is why your expansion factor is 1 minus 2 all over 2. So this gives us a value which is negative 0.5 or negative 1/2 for our expansion factor. Now, we have determined already the very important expansion factor. Now, we need to know whether we know where to go or we know the next step that we're going to use in determining the rate equation. What do you think would be the next step that we will be doing in here? So I already have the epsilon A. What do you think is the next step? Marcel? Any suggestion, Marcel? Okay, so let's see. So Giselle is already writing on the chat box. Marcel, are you there?
Hello, Miss.
Yes. What do you
Mm.
think should be the step that we'll be using here?
I-substitute siya, Miss, sa equation.
Equation. Okay. What equation would that be, Marcel?
Miss, CAO over epsilon, epsilon, over EA, the expansion, over EA, Miss, LNV over V sub 0, V sub V naught.
If you're going to use that equation, Marcel, we don't have the entire data to use. So far, what data do you have? You're only given the epsilon, and based on the given here in the problem, you have the epsilon already determined, that's not given, and this, and this.
Okay.
So if you intend to find something, if you want to find something, it should be based on what you're provided with. Okay, remember that you are after the rate law. So actually, if you have the copy of your book, you would know what to do, because I know this is in the book, but that's not the kind of thinking that I wish you to embrace, because the book knows where it's going to, because it's the author who's writing it. But nonetheless, I'd like to check whether, if you're not looking at your book, and if you're doing this as a student, what do you think would be the next step? Not as it is outlined in the book, because the authors know what you're supposed to determine. But if you're a student, if I put myself into your shoes, what do you think should be the next step that you will be doing? Because you have in mind that you will determine the rate equation. The author of the book knows what should be he needs to determine first, because he's the author. He almost know everything that he have written there. But if you are a student, you don't know anything yet for now, but you have to know where you are going. So I'd like to know, what are you thinking now if you are asked to determine the rate equation? What is it that you will be determining or calculating? Actually, if I'm a student, I will not determine the CA in relation to epsilon A, because that will not directly point me to what I'm looking for. I think I'm now directing you to the direction in which you should be going. So what do you think should be the next step that you should write here? That way you will have a sense of direction on how you're going to determine the unknown, which is the rate equation. Not as dictated by the book that this should be the next thing that I should determine, because the book says that that should be the next step. Naturally, because the book knows where it's going to. What do you think should be the next step? I'd like to know if somebody knows how to find his way through the maze of a particular kinetics problem without having to rely on a solution that is provided by the book. Anybody? If I will not start with the CA, anyway, I would still go there if I do not know. What should be the next step that I should be doing? The first step that was suggested by Colleen is correct because we don't want to forget this. If we forgot this and go on solving, everything that we'll be doing is wrong. So this is a correct step. Okay, what do you think should be the next? If you're a student, you don't have anything to use when you solve a problem, but you only have your critical thinking skills. What do you think should be the next step that you should be using? I have given this particular key equation to you at the end of the topic on the design of reactors. What is this equation? Chat box again. Determine the K. Katrina, determine the K C sub A raised to N. Very good, Katrina. You need to get the rate law. That way you can get the rate equation. Because anyway, I mentioned it a while ago. So very good, Katrina. You need to find this. Now, if you need to find that, that would bring about you looking for this and this. You can only find these two if you have this already complete, or if you have a way of determining this rate expression, because if you have this rate expression or rate value, you can find the K in the end based on the topic that we have ended with in integral and differential analysis. Okay, if you recall differential and integral analysis. But for now, I will accept this direction that Katrina is telling us. Miss, I'll go for this. I'll find the rate law because I can rewrite this in the form dCA dt equal to K C sub A raised to N. From my rate law, I have my rate equation based on the way we have distinguished one from the other. Okay, now, if this is what I want, as Katrina is saying, where will I get this based on what you have learned? Where can we get this rate? Where will you solve this rate? Or where should this be coming from? That's the fundamental key principle that you should not forget in reactor design. And we have ended with that particular equation. What equation will we use? Now I'm asking for the equation. That way I can find this. What equation is that? What equation is that? Anyone? You need, oh, thank you. You need in terms of conversion, Miss, RA equal to C in terms of conversion, si Earl, the empirical rate equation is, okay, empirical rate equation according to Joshua, determine the K. Before we can determine the K, what will we do first? You cannot determine the K, you cannot determine the N before writing this. You need to write this one. What is it that you need to write? You need to, that way, the suggestion a while ago that I will write the CA in terms of XA, that would be the next step actually. So let me read again what is here. No, not yet. You need to write the performance equation of your, you need to write the performance equation of your MFR. For an MFR, your performance equation is volume over volumetric flow rate is equal to the amount converted or reacted all over the rate. Isn't it that in this particular expression, I have this, and this one is this? So you need to find this from here, from your performance equation, right? But this one This one has this particular XA here. You see this XA here? This XA is different when you have a gaseous reaction rather, wherein you have a fractional change in the volume, or you have the expansion factor. It's different. So that's the reason why. So some of you suggested that. So I will have this as the second equation. So I will have this as the first equation. This is the second equation, which I need to go back to. And I need to have an XA. An XA based on the formula that was suggested a while ago, or that was mentioned a while ago. What is that XA formula? Sheet 3. That is XA formula. So you know that you need to find this. In order to find this, you need to use this equation. For you to be able to use this equation, you need to substitute the correct conversion. Okay, not just any conversion, but the conversion when you have a gaseous reaction. That's the next step that we're going to go to. So what should be the XA in this case? So Marcel was suggesting a formula a while ago. However, it's dependent on volume. We don't have volume. So what should be that formula? You have, okay, you have Ca. In our original expression for Ca, we have CaO 1 minus Xa. That is if we don't have a fractional conversion or expansion factor to consider. But since we have now, isn't it that we altered the denominator by writing 1 plus epsilon A Xa? Okay, we write our denominator in this manner. Then we determine the corresponding formula for XA. Now, in our PowerPoint presentation, it was given already what should be the formula for XA for variable volume reaction. Now, so that we will not anymore derive, but we can actually derive. So you have Ca 1 plus epsilon A XA is equal to CaO minus CaO XA. You wish to group the terms which has the XA. So you have the Ca plus Ca epsilon A XA is equal to CaO minus CaO XA. You wish to find an XA formula. So you have Ca minus CaO. Transfer it here, and this one I will transfer here. So you have negative Ca epsilon A XA minus CaO XA. That way we won't have to deal with the negative sign. So I will interchange these two. So you have CaO minus Ca is equal to XA. Then I will have Ca epsilon A plus CaO. Now I have a formula that will determine XA. So XA is equal to CaO minus Ca all over Ca epsilon A plus CaO. Now this is the third equation that you have. That way you can solve for XA. Why is XA very important? Because you will substitute it here, sorry. You need to substitute it in here together with the other values. That way you will have RA. It would look like, class, you have, if we will substitute 3 to 2, we will have an expression for XA. So we will do that. That way we only have one formula. I have skipped one. Oh, anyway. So you have this particular XA formula. Then we go to the formula that we have V over VO is equal to CaO. The XA that we'll be using is this XA formula here. CaO minus Ca all over I'm copying this one. So FCA epsilon A plus CAO. Plus CAO. So this is for, isn't this whole thing is for the XA, and you have here the rate expression. I want to know the rate. So my rate would be, so my rate, this rate is, transfer it here. So you have CAO minus CA, this one. And this one you transfer here. So that would be small v sub O. This one we place here. So this is V times the quantity CA epsilon A plus CAO. Now, since you have 4 runs, in your 4 runs, you will have to determine the rate and the CA pair. Now, the CA is already given in the problem. This is already our CA. So all you have to do is copy the 4 CA values that were given. So I'll place the 4 CA values here. So you have an 85.7, you have a 66.7 again, and you have a 50, and you have a 33.4. You need to get the RA based on this data that we have. The problem gives us the CAO, it gives us the volume of the MFR, and it gives us also the volumetric flow rate for each of the 4 runs that corresponds to this particular final concentration. And we were able to determine the epsilon A. Now, with all this information known already, you can solve for the 4 RAs here. Can you please do that? So we have the 4 RAs here. Kindly solve for the 4 RAs. You substitute CAO. So I'll place the given here. The CAO in the problem is 100 millimole per liter. And then the volume is 0.1 liter. The epsilon A we determine to be negative 0.5. As for the volumetric flow rates, so for the 4 runs that we have, so this run will have a 10, this one will have a 3, this one will have a 1.2, and this one will have a 0.5. So this is the volumetric flow rate. So with this set pairing here, and with this, you can determine the rate. Can you please give me the values for the 4 different rates of reaction for the 4 runs? Okay. Just sell the first, the 1.2, the, is this 1,000, what is this just sell? Renzo, the 2502.19, this is for what? For what run?
For 85.7, Miss.
Thank you. So you have
Ang first, Miss.
2502.19. So we need, just sell this, what is this? 1 point, what is 1,000? Ano na siya man? Kay apat man ka number after some point. Okay. Sige, sige. Please solve for the next 3 runs. Thank you, Renzo. Second value, please. Trisha. Oh, pareho ka mo ni Jabame. So you have 14, thank you, 1498.87. The third is last run si Earl. Thank you, Earl. 399.76. The third run, Trisha, correct man. Pareho ka mo ni Jabime. So 800. So there's also a marked decrease. You could see the trend also that there's a decrease in the rate. I think you know what is forthcoming of this. So you already have the rate and you already have the concentration. Remember, that's the first thing that I asked from you, and which Katrina said is, I'd like to find this one so I can find the rate equation. So I already have the rate and the CA. How do you find the K and the N? How do you find the K and the N? You will make another table. LN, miss. Correct. So you get ang values kaina naton, you get the L. Don't mind my negative there. There should not be a negative. So you get the ln of CA and the ln of the rate. Okay? So if you get the ln, so you use these ln's that I have here and the rate. Now, if you do that, so please take note of the values. If you do that, it's like getting the, if you have this rate here and you have the K C sub A raised to N, okay, as a review, we've discussed this, that we will get the ln of both sides of this equation. Then you will have the ln of the rate equated to, since we have the product of these two, the ln of the K plus, so product means addition of ln's, CA, where this n here in the exponent is the multiplier here. So this is comparable to a y. This is comparable to an x. This is comparable to the slope of the line, and this is its corresponding y-intercept. Okay? So I'll go back to this one so you can give me the values of the ln. So please get assigned to siguro para dasig. For ln, the ln's of CA, Sarah for the first value of LNCA, Rona for the second value, Mary Lynch for the third, and for the fourth, we'll have Marshall. For the LN of the first RA, we will have Jules. The LN of the second RA will have Joanna. The third RA should be Eugene, and the fourth would be Antoinette. Okay? Just give me the ln values. So we will now have to end with a very simple process of linearization. Okay? So do we have the ln of the first CA already? Okay, wait. First value, 1.933. Correct na siya, Joe Byrne. Hindi lang tagali mag-plot. Maano lang ta? Best fit line equation. Second value for the LNCA, please. Thank you, Sarah. Second value for LNCA. 3 minutes na lang. Please hurry up. Third value for CA is 1.669699. Wala ta second value. Inutong inassignan kung sa second value nalipat na ko. Fourth value, same with RA. Kung may nakasolve na dasang RA ng LN. First RA value, 7.312. Fourth RA is 5.991. So, thank you, Antoinette. Joanna, second RA is, ay, second ni gali, 7.8 gali. Sorry, hindi lang ha. Hindi mo. Ang first nga RA, second RA na siya ang 7.312. 7.8 ang $8,249. Ang fourth RA, second RA, first RA. So, Eugene, ang third nga RA, 6.68. I'm looking for the second LNCA and the fourth LNCA. Sino itong din-mention ko man? Third CA, why na di ang second kag ang fourth nga CA? Sige. Joshua, can you solve na lang the LNCA, the second LNCA, and Jobern, the fourth LNCA? Wala, siguro kabati itong duhangin tawag ko. LNCA for the second value and LNCA for the fourth value. We're going over time. Fourth CA, nakalag, LN talang pala para riho. Sige, Sarah, islan talang. Fourth CA is 1, ay lang nagsaka. LN 4.45 ni siya, Sarah. Oh. Okay, wait. Second CA is 4.2. Thank you, Rona. And third value is 3.912. So, islan ko ni. The fourth niya, naku to fourth CA. Di na to siyang fourth CA. LNCA. Fourth. L 3.5. Thank you. 3.5086. So here we go. We're complete. So the values of the LNs of the two. Then you can use the best fit line equation. You use your calculator to get the equation of the best fit line. The slope automatically gives you the M. And the y-intercept gives you the L and K. So for the B, the N is the M. And for the B, I still need the B, and the K is, of course, your E raised to B, because this is ln of K. Sige. What is our slope? Okay, have here. M is, which of the two is correct? 1.9. Okay, I'll go for the 1.95, Renzo. It's more or less 2. Or you can write n being equal to or more or less equal to 2. Or 1.959 if you want. Correct. What about for the y-intercept? Or can you solve for the k? You make that as the exponent of the e. K is 7.09. This is more or less 7. Okay, if that is the case, well, my favorite number get 2 and 7. So then we have the rate law. We can write the rate law as 7 C sub A raised to 2. Or if you want to write the rate equation, that would be dCA dt equal to 7 C sub A raised to 2. Then you have to specify the units. Since you're using millimole per liter, and our time there is hour, I think. So since our volumetric flow rate is in hour. So this is our rate equation. You took it from the performance equation of your MFR. So hindi gid paglipatan ng performance equation. When you're lost, you won't get lost further if you start writing the performance equation, because that will give you a sense of direction. Based on your performance equation, you will see what you need to find prior to getting the required information that the problem is asking from you. However, the suggestion of Colleen, that we will start with the expansion factor or the fractional change in the volume, you should also remember, because if you forget that, you will be getting a very different set of results for your N and K. So I'll go back to the slide.
Hello, miss.
Yes.
Amo na sang answer, miss, no?
Yes. Amo na
Ano,
nasang
miss,
answer.
base wala na confused. Wala, miss, ako. Kay, ang gakakuha ko nga value nga y-intercept is nga ang k, bala, miss, 0.39. Okay? Hindi siya 7.09.
Wait, check ta. Mary, di may get shot. Same for me. Hindi siya 7.
Oo, miss.
What's your answer, Joshua? 0.3986. Then that would be it. So, sala si Earl, wala siguro ma-erase to kay 1.959 gamit ko.
Balian mo na siya, miss, gali ang slope, miss.
Ang ano? Ano ang
1.959.
Ang 1.959, that's the slope. Yes. But the y-intercept that you're getting is not yet the right away your rate constant. You still need to make that as the exponent of the e. Kada ko gali isang difference if you use the 1.959 and the 2. Anyway, we'll go for the 0.3986. So we'll go back to our board. We'll correct it. So we'll change this one. Since this will be recorded, so you can go back to this. So that would be, in this case, 0.3986 C sub A raised to 2, or 0.3986 C sub A raised to 2. I used the 2 because I think that's the answer that is being used in the book, but I did not recall what would be the corresponding K values, because sometimes when I solve a problem that has a written solution, I'll just get the answer. That way I can compare. But I only recall the order, which is 2. I forgot the rate constant. But nonetheless, you can always double check, because this is a sample problem from your book. So you have this as the rate equation. The one that you have on top is the rate law. But the answer that was provided also was the rate law, because automatically you can change the R sub A expression on the left side, the negative R sub A expression on the left side, by negative dCA dt. Okay, I'll go back to our slide. We'll just have a break after this. And this is the problem that we've worked out. Actually, we have 4 problems. I intend to really ask questions. That way you will understand better, rather than me talking in monologue. And you get to think rather than me thinking for you. So you have example 2, and these are the key points that you have learned. So it demonstrates that we will have to need multiple runs, just like what the problem gave us. It gave us 4 runs. in a mixed flow reactor to arrive at a reaction rate expression. So it's impossible when you're provided with an MFR problem that it would ask for a rate equation giving only one set of data. So there have to be sets of data. That way you can answer the said problem. And this one is the first step that already Colleen suggested we never forget. So we don't ignore density changes. Ignoring density changes meaning you don't solve or calculate for the epsilon A value, the expansion factor or the fractional change in the volume. If you've ignored it, that will give you a wrong kinetic expression. So we will leave this link now, class. I will stop sharing and I'll stop